Today we start that chapter that is the rotatory motion or rigid body dynamics. So this rigid body dynamics is one of the important chapters in first year physics. Generally, why that rotatory motion is considered to be difficult? Because it is always involved with the number of multi-constituent. So that is generally Newton's laws of motion, and again that friction, all these are involving along with this rigid body dynamics. Now here first we are coming to this moment of inertia. So this moment of inertia, what you call it is the rotational inertia. But to understand this moment of inertia, so first we have to know about this linear inertia. Linear inertia means it is the inherent property of a body by which it cannot change its state of rest or a state of motion or the state of direction by itself. State of direction by itself. Similarly, that is for the bodies which are traveling along the same straight line. Suppose if at all the bodies which are rotating, so which are rotating like this, they also possess the same property that you call it is the rotational inertia or the moment of inertia. And these bodies also, as far as possible, they always resist the change in direction. And if at all that external agency which tries to change the direction, if at all it is more dominating, then only it changes its direction. So that you call it is the moment of inertia. And that moment of inertia, that depends upon so many factors, that moment of inertia. Suppose here it is a rigid body we are taking, and this rigid body there are number of particles are there. This is the m1 is here, and again the m2 is here, and this is the axis is there. This is the axis of rotation. And with respect to this axis, the body is rotating. Now here m1, m2, m3 like this, all these are maintaining the distances, different distances, r2 and again the r3 like this. Now this can be taken as the I is equal to m1 r1 square plus m2 r2 square like this, and it is going up to this, that is a sigma mi ri square, and it is the I is equal to 1 to n. And the general formula can be taken as the I is equal to mk square, where k is known as the radius of gyration, where k is called the radius of gyration, and it is the effective distance of all the particles from the axis of rotation. K is known as the effective distance of all the particles from the axis of rotation. Now we are coming to this today, that is the moment of inertia of different rigid bodies. Moment of inertia for different rigid bodies. Different rigid bodies means, suppose first of all moment of inertia, it depends upon so many factors as I already told you. Suppose for example, for the same body, if you are changing the axis of rotation, that moment of inertia changes. For the same body, if you are changing the axis of rotation, that moment of inertia changes. For example, if you are taking that circular disc, and for the circular disc about its natural axis, the formula is the mr square by 2. And again, when you are coming to that about the diametrical axis, it becomes the mr square by 4. Like that, for the same body, and depending on that axis of rotation, that moment of inertia is continuously changing. So that's why what we can understand, it depends on axis of rotation. And the next one is, here we are maintaining that axis is a constant, and mass of the body is also constant, but depending on the shape of the body, again that moment of inertia may change. For example, if you are taking, this is the circular disc is there, and the circular disc having the same mass m, and again it is the axis of rotation is the natural axis is taken, and that formula can be taken as the INA is equal to mr square by 2. And suppose if you are taking another body having the same mass, we consider it is the uniform rod. That is a uniform rod. Even for that uniform rod also, if you are maintaining the same mass, but here about the natural axis, here the moment of inertia will change, and that can be taken as the ml square by 12. INA for the uniform rod is the ml square by 12 like this. Its meaning is, that's why it depends upon the axis of rotation, and it depends upon the for the same mass, and again the axis it depends upon the shape of the body, and these are kept constant and depends upon the shape of the body, and it may be uniform rod, it may be uniform disc like that. It depends upon the shape of the body. And now we are maintaining that axis is the constant and mass of the body is also constant. Axis is the constant and the mass of the body is also constant, and again that the shape of the body is also constant. Even then there is a possibility for the moment of inertia to be changed. How it is possible means now we are taking this is the body is there, and here this body is that is a circular, that is a hollow spherical body is there, or now here you are taking some particles nearer to, so at these positions if you are taking some particles here, and this is the axis of rotation like this, and here you can have some moment of inertia. Here you can have some moment of inertia, and suppose if these particles are shifting towards this to this position, in this case suppose if they are shifting to this position, in this case again you can have another moment of inertia. Its meaning is in these two cases we did not change the mass of that body as well as that axis of rotation and shape of the body and the mass of the body, but even then you can have that change of moment of inertia. Then what we can understand that moment of inertia depends upon the mass of the body and the axis of rotation and the shape of the body and again the distribution of particles within the body. So on all these factors moment of inertia depends. So distribution of particles within the body. Now here in this class we are going to discuss what are the moment of inertia of the different rigid bodies. So of the different rigid bodies means first of all we start from that uniform thin rod. That is a uniform thin rod we are taking. So generally for the natural axis, so other than for the natural axis, to find out the moment of inertia of a natural axis, then we have to take the help of integration process. We have to take the help of that integration process. If you want to find out the moment of inertia of any rigid body that is about the natural axis, we have to take that integration process except in rectangular lamina. Except in rectangular lamina. In all these cases our requirement is the integration process. Suppose for example if you want to find out the moment of inertia of that uniform thin rod, so this is the uniform thin rod is taken and its mass is the capital M is taken and again its length. Now we are going to find out this is the natural axis. Here in case of the uniform thin rod the natural axis is defined as it is the axis which is passing through the center and perpendicular to the length of the rod. So it is passing through the center and perpendicular to the length of the rod, that you call it is the natural axis. So to indicate this is rotating about this axis, that's why we are giving such type of arrow like this. Now here this can be taken as the minus L by 2 and again this can be taken as the plus L by 2. And to find out the moment of inertia of such bodies, then first of all we have to take some element like this. This element can be taken as the dx is the element. Dx is the element. Now we are already we have assumed the mass of the entire rod is the m. Now we have to find out that is the mass of this element. And here this element is located at a distance x from the axis of rotation. From the axis of rotation. In this case now it is the m is the, so complete length is taken, m is the mass. And if at all dx is taken, then what is the mass means that dm is equal to dx by L into m. So dx by L into m. So now we are finding that moment of inertia of this. We are finding the moment of inertia of this element only about this axis of rotation. And for that we are taking the di is equal to dm into x square to be taken. Dm into x square, because the general formula already we know it is I is equal to mass into distance square from the axis of rotation. So that's why it is the di is equal to dm into x square to be taken, and here dm in place of that dm what we are applying, that is the dx by L into m x square to be taken. And if you want to find out the moment of inertia of that entire uniform rod, if you want to find out the moment of inertia of this entire uniform rod about this axis of rotation, then you have to integrate it in between the limits, and that's why it is taken as the m and again the by L, these are the considered to be constants, and again here it is the integral x square dx, and that dx can be taken anywhere along the length of the rod. So that's why the limits can be taken as the minus L by 2 to plus L by 2. So minus L by 2 to plus L by 2 to be taken. Now integral dA is equal to I to be taken, and again it is the m by L is here, and thereafter integral x square dx means it is the x to the power 3 by 3, and as usual that is the L by t, and again the minus L by 2 to be taken. And here regarding that integration, now what is the formula that we have applied here? That is nothing but integral x to the power n dx is equal to x to the power n plus 1 by n plus 1. That's formula is to be used. Now it is the x cube by 3 is here. Now this can be taken as the m by 3l, and after that when you are applying that upper limit, that becomes the L cube by 8, and again when the lower limit, that becomes the minus L cube by 8 to be taken, and overall it becomes the, that is L cube by 8 plus L cube by 8. Now it becomes L cube by 4. So overall it becomes, it is the ML square by 12, and what you call it is the INA. That is the moment of inertia of the uniform thin rod about the natural axis is the INA is equal to ML square by 12. It is the ML square by 12 to be taken, moment of inertia of the uniform thin rod about this natural axis. It is the ML square by 12. So first of all, once again I repeat you, that is the, here the natural axis is nothing but the axis which is passing through the center of the rod and perpendicular to the length of the rod. So like that. Similarly, we can find out the moment of inertia of the different rigid bodies. Suppose for the uniform thin rod, if you want to find out the moment of inertia about other axis, means suppose here what we have taken, this is the uniform thin rod that is rotating like this with respect to the natural axis, or it may rotate like this also. In this case, how to find out the moment of inertia of this uniform thin rod about an end? Then you have to take the help of either the parallax theorem or that perpendicular axis theorem. In this case, a parallax theorem is required. In this case, so that's why other than that natural axis, suppose if you want to find out the moment of inertia of the same body with respect to the different axis, then you have to take the help of either the parallax theorem or the perpendicular axis theorem. So that's why in this case what we are taking about the thin rod also, that is for this thin rod about this end, then it is taken as the total length can be taken L to be taken, and already we know this is the axis of rotation. Now here this is the natural axis, already we know the distance between them is the L by 2 is there. The distance between them is the L by 2. Now it is the moment of inertia about this axis of rotation. Now the two axes are appearing here, but you are going to find out the moment of inertia about this axis only. In this case, we are applying the parallax theorem. That parallax theorem is nothing but I0 or the I0 is equal to Ig, and that is a passing through the center of gravity. Ig plus mr square, where r is the distance between the two axes of. So where r is the distance between the two axes. Now Ig is equal to, that is nothing but the INA, and it is the ML square by 12 is here, and plus m, and r is nothing but the L by 2. That distance of separation between the two axes is the L by 2. So that's why this can be taken as the L by 2 whole square, and overall on solving you are going to get that I is equal to ML square by 3. That's why the moment of inertia of this uniform thin rod about an end is the I end is equal to ML square by 3. So here it is the ML square by 12 is there, and ML square by 4. When you are taking that LCM, you are going to get that ML square by 3. So that's why uniform thin rod, you can have the two axes. That is the, you can have that moment of inertia with respect to the two axes. One is about the natural axis and the second one is about an end, like this. So that's why uniform thin rod is over. Now we are coming to this moment of inertia of that circular ring. So for that circular ring, if you want to find out the moment of inertia of that circular ring, again you can have that, that is for this circular ring, it is the about this natural axis means. Natural axis, you have to take that help of either the integration like this, then you have to find out that INA is equal to, this can be taken as the mr square for the circular ring, where r is the radius of that ring. M is the mass of that ring. So this is a circular ring to be taken. And here, how do you define that? That is the, that is the natural axis in this case. The natural axis in this case of that is a circular ring is, that is an axis passing through the center and perpendicular to the plane of that ring. So passing through that center like this and perpendicular to the plane. So this is considered the plane. So that's why this is said to be the axis passing through the center and perpendicular to the plane of this ring. That you call it is the natural axis. So that's why it's taken as the natural axis. In this case, it will be taken as the natural axis is here, and NA. INA is equal to mr square to be taken. And in this case, after that, INA is equal to mr square, that is the first formula. And again, if you want to find out about the diametrical axis, diametric axis. Once again I repeat you about the natural axis in this case is an axis passing through the center and perpendicular to the plane of that ring. This is set to the plane. So perpendicular to the plane of the ring means like this. So that's why INA is equal to MR square to be taken. And when you are coming to the second one is, that second one is here it is about the diametric axis. Then you have to take that help of perpendicular axis theorem. So diametric axis means, suppose if you are taking this one is here, and now in this case this is another one diameter, this is another diameter, and this diameter is taken along the x-axis, this is taken along the y-axis like this. Now that's why it is the, already we know that according to the perpendicular axis theorem, Iz is equal to Ix plus Iy to be taken. And here it is the Ix is there and Iy is here and Iz will be like this. That Iz is nothing but the natural axis of the ring only. So that's why in place of the Iz, what we are taking, this is the INA, and Ix means I diametrical axis plus I diametrical axis is here. And that's why it is the I diametrical axis is equal to, it is the MR square by 2 to be taken. I diametrical axis in case of the circular ring is the MR square by 2 that is to be taken.